So we need one more thing to finish mean shift tracking. You remember before when I was showing you the mean shift example, we were plopping down a circle, right? And I said, we'll worry later about the shape of that. Well, that circle can be thought of as a uniform kernel. What I mean by uniform is that its height is the same everywhere around, and it happens to have a circular shape, and it would be written like that. That's not such a great kernel. What do you think a better kernel might be? Well, instead of using the uniform kernel, we could use something that is differentiable. We'll use that in a minute. Isotropic, all that means is that it's the same in every direction. Monotonically decreasing kernel, and there's a certain convexity property. You're not going to worry about that. So what's our favorite differentiable, isotropic, monotonically decreasing, always positive kernel? Yes, it's the Gaussian. Okay. So here it's written just as a constant proportional to a fall off by the square of the distance. Okay. You can also have a scale factor, right? So if you wanted, you could talk about like the sigma, sort of the scale of the kernel. What's really cool about this is that unlike the uniform kernel, which goes straight and then falls off on the edge, this is differentiable, okay? You can know how much it's changing, and it also means that it goes down to 0 at the edges. So as you slide that kernel along, a new point, it just has a very, very small weight. In fact, an infinitesimally small weight, and then it grows. Likewise, points that are right near the top, their weight doesn't change very much, right? Because as you slide it along, the weight stays about the same. The points that are going to have the greatest value are the ones that are along the slope. What that means is you can know how your function changes as you move. That is your overall function, so your Bhattacharya coefficient, for example. And what you can do is you can use this gradient to essentially hill climb up your similarity function. Right? So you can, by computing this, you don't have to sort of blindly search. You can actually follow that gradient and get to a local maximum. All right? And that was the basis of mean shift tracking. So now, going back to our previous example here of the ping pong, right? We start with the current frame. We want to search, but now our search can actually climb to the maximum of this function using that gradient information. And that's mean shift tracking.